Namaste, welcome back after the break. Let's continue where we left off earlier. Just a little bit of overlap with whatever we have discussed before the break. I want to once again go through the features, the Verilog features, and explain to you all these things once again. Okay, higher abstraction means absence of details. It is required to have as few details as possible initially, so that we get a good idea and execution of simulation is very quick. Therefore, we write code at the behavioral level, also called RTL. This is technology independent. When I say technology independent, it means that I can take the same code and target it to make a chip at a different technology node with a different process node, because it doesn't contain Verilog written at the behavioral level doesn't contain any technology dependent factors like the delays of the gates, the sizes of the gates, and anything. It is pure functionality. There is no timing involved. Okay, this behavioral code, the RTL, you can make it operate at 1 gigahertz or 10 gigahertz also by just having a clock of that particular time period. That's it. You can make it work. It's pure functionality. Timing will come into the picture only when it has been synthesized and the elements, logic elements, have been picked up from a technology library, and these logic elements will be actual physical logic elements whose representation is identical to its behavior in hardware, but right now it is representation in software. Right now means in the library it is a software representation of a hardware behavior. Okay. Then netlist level simulation is much slower than RTL level simulation, and therefore RTL level simulation needs to be done extensively in order to verify 100% or maybe 110% of the functionality, and netlist level simulation is not really done extensively because it will take days and days together to complete a simulation run at the netlist level, because so much of calculation, computation of the gate outputs, delays, interconnections, interconnect delay, all these things are required to be computed, that it will take an extremely long time when we are dealing with chips at the million or a billion transistor level. It's very difficult, so it's not done there. Now for this particular, in this session we will talk about the VLSI manufacturing flow. When I talk about VLSI manufacturing flow, I am referring to the ASIC manufacturing flow, because the tools that I will be mentioning later on in this session are the ASIC tools, ASIC development tools, not the FPGA development tools, because FPGA development tools, there is a difference between the ASIC development tools and the FPGA development tools. Let me highlight those differences over here, and possibly I'll make a slide. I haven't made one, but I'll make a slide to put it in black and white. What are the differences? But the primary difference is the ASIC development tools are meant for production of a chip, for a manufacturing of a chip, whereas FPGA development tools are meant for putting a design into an already constructed, fabricated, manufactured part called FPGA. Therefore, third party vendors like Synopsys is not a manufacturing, it's not a fab. Okay, Synopsys is an EDA tool company. Okay, therefore ASIC tools are typically developed by some other companies called third party vendors, whereas FPGA tools are developed by the FPGA manufacturer itself. That means, for example, take the case of Xilinx. Okay, Xilinx comes to my mind because I was earlier working with Xilinx. So Xilinx makes FPGA. Of course, now Xilinx has been taken over or acquired by AMD. But Xilinx makes its own FPGA, gets it fabricated. The FPGA is fabricated from, let's say, fab companies like TSMC in Taiwan Semiconductor Manufacturing Corporation. So it gets it manufactured from Taiwan, but the software that is required for the users of these FPGAs is developed by Xilinx itself. It is not developed by somebody else, by a third party, because Xilinx knows exactly what is inside the FPGA, what are the resources available inside the FPGA in terms of logic gates, in terms of flip-flops, in terms of mega cells like a DSP block, in terms of interfaces like a USB interface, PCI Express interface, or also in terms of interconnect resources, what are short resources, what are long resources, what are the clock routing resources. All these things Xilinx is aware of the internals of its FPGA. Therefore, it would not want any other software developer to know about the internals and develop the tools. So Xilinx tools, like for example the ISC of the previous years, or now Vivado, is developed by Xilinx itself, so that this software can make full and the best use of the available resources inside the FPGA. Therefore, while FPGA EDA tools come from the FPGA developer itself, the ASIC EDA tools come from third parties. Okay, not necessarily. So if let's say Cypress Semiconductors was manufacturing a chip, it will be using ASIC synthesis tools from either Cadence or Synopsys or many other names which are there prevalent in the market today. Okay. Coming back, this is an ASIC design and manufacturing flow that I will be talking about. Okay, that the specification is given to the design group and the verification group. Both of them read through the specification. Both of them read through the specification and try to understand the specification. This diagram has been simplified. That's why I will say a simplified overview of the ASIC design and manufacturing flow. That's what I will consider the title for this session to be. Now, when you when the specification goes to the design and the verification group, both of these read these specifications, and that reading and understanding may go on for several weeks. It is not as if they read it in one day and the next day they start designing. No, it's not like that. They not only read that, but they try to come to an understanding of what the specifications mean. The design group and the verification group may sit together and try to discuss their own understanding of the specifications. Why is that specification given to the design group as well as to the verification group? Is because the design group may have an understanding of the specification in its own way. Verification group may have its own understanding of the specification, and these should match completely, because based on the understanding of the specifications by the verification group, it will come up with a test bench. It will start developing a test bench and for the design that is going to come. The design, in the meanwhile, the design team would start working on breaking down the design into sub-blocks, trying to identify the interfaces that are necessary for communications between the sub-blocks, and all these things will go on. The verification team has to develop a test bench, and it has to apply the inputs to the design that is finally going to be verified. But initially there is no design that is available to be verified, and therefore what the verification group does is it will generate what is known as a bus functional model. That means at the pin level, what is going to be the behavior of the block. That kind of a behavior is developed by the verification group. They develop what is known as bus functional model of the particular design, not going into the internals, not knowing about the flip-flops. Just that if a particular input is given to the design on a particular line, then the output is expected after, say, let's say 23 nanoseconds or 24 nanoseconds or whatever it is. Accordingly, the verification group will generate an output for after 24 nanoseconds. Whether that output was generated as a result of flip-flop or as a result of some other combinational logic inside is not important for the verification group. It develops only bus functional models, which are much simpler to write compared to the detailed design, simpler and less time consuming. Therefore, they will be able to come up with their own bus functional model of the block and write and use it on the test bench, or use the test bench on that model. By doing that, what they are doing is they are also evolving that test bench. A test bench, once you write, it's not just over and you just throw it to the design team and say that this is the test bench and this is how you have to verify. Or for that matter, the design team will not be able to design it in just a week or a few days and just throw it to the verification team to say that go ahead and verify. No, it is a long drawn evolving process, and this needs to be taken proper care of. Then once all this exercise has been done and you come to a point where now we feel that the design team feels that it is time to go ahead and do a design and design entry. Design entry means what? The design entry is the action, is the part where the design actually gets entered and gets resident or stays in an computer system. The design stays in a computer system in a software form. Okay. Now that software form can either be in the form of a Verilog HDL, Verilog language, or it can be in the earlier years it was schematic capture. Schematic capture means drawing logic gates, interconnecting them on the system and all that. We had in the previous years, we had software like PCAD, ORCAD and Tanner, LEdit and so on, the software which were there for schematic capture. So the design was captured at a schematic level, that means at the logic gate level, and then stored into the system through the interconnections. Okay. Whereas currently not many, or only if the design is very, very small and it needs to be entered, it could be entered as a schematic, but it is much easier to write it in a Verilog language, okay, and have it pass through the synthesis tool, so that the synthesis tool will generate the required gates and their interconnections which adhere or which stick to the functional specification or to the functionality of the block written in Verilog HDL. So that's how it is done these days, and this is done at a high level of abstraction, and the underlying logic is not assumed to be in any form, in any technology or whatever it is. For example, if you want to write the functionality of an adder, what you have to write as the main statement or the main execution statement of the Verilog code is like y is equal to a plus b. That's all. A could be an 8-bit quantity, B can be an 8-bit quantity, and Y can be a 9-bit quantity. As you all know, if you add two 8-bit quantities, you will get a 9-bit quantity. Therefore, you simply say Y is equal to A plus B, and then you provide values through the test bench. You provide values to A and B, keep changing them at periodic intervals at some times, and then you will see that the output also changes accordingly. But are we assuming what type of an adder is being used there? No, we are not assuming there. We are not assuming the presence of a ripple carry adder, or the presence of a carry look ahead adder, or the presence of a carry save adder, carry select adder, carry skip adder. There are so many different types of adders. Are we assuming that there will be a ripple carry adder, one of the basic adder structure there? No, it is not. What happens here is that the computer executes this statement by executing a series of software assembly language instructions. A and B are nothing but memory variables. They are stored in the memory, they are fetched from the memory, they are added in the accumulator and stored back into another memory variable called Y. That is how it is executed. It does not have a carry input, it does not have a sum output and a carry output. All these things are not assumed. Simply a software execution of a statement is done at the RTL level. Therefore, no details are involved here. That is the beauty of writing code in Verilog HDL. Once that is done, the code is written to some extent. Different blocks will be allocated to different people in the design team. They will write their own code, and their own interfaces have already been defined. And the designers also do what is meant by sanity level checking. That is, they write a simple test bench for checking that their code prima facie means basically is working okay or not. Once that is done, with some test cases they will use, they will then give it to the verification team for more exhaustive and extensive verification of that particular block. We are not talking about very simple blocks which consist of only one counter or one multiplexer or a counter and a multiplexer. Blocks are reasonably complex, typically of the order of about 3K, 4K or 5K gates. It could be like that, 5,000 gates. Okay, when synthesized they might come to about 1,000 to 5,000 gates. That is the complexity of the blocks that we may need to subdivide into. Okay, not anything lower than that, because the more you go lower and lower and make it more and more simple, the number of interconnections between the sub blocks increases. Okay, so therefore we should not be completely at the top level and have no interconnections between the blocks at all. At the same time, we should not be so simplistic for each block that there will be a huge number of blocks which need to be interconnected. So in between somewhere, to a moderate level of complexity, the blocks are subdivided. Once that is done, a behavioral level simulation is done. Now for doing what is meant by simulation, I have a slide which tells what is the difference between simulation and emulation. Okay, I will talk about that a little later, but right now we are concentrating on simulation. Behavioral simulation, behavioral because this code has been written using Verilog at the RTL level. Verilog can be written at various levels. Let me mention here, a small digression, let me mention here that Verilog can be written at the RTL level, many behavioral RTL level. It can be written at the gate level. It can be written at the switch level also. Okay, there is intermediate one more level called the data flow level. At the behavioral level, which is the highest level of abstraction, data flow level, slightly lower level of abstraction, gate level, and at the switch level. Gate level means you have gates written like AND gate, OR gate and all that, and at the switch level you have keywords like PMOS, NMOS or CMOS and all that used, and you can write Verilog code at the switch level to also describe an AND gate. You can write Verilog code at the gate level to describe an AND gate. You can write it at the data flow level to describe an AND gate, and you can write it at the behavioral level also. Sometimes for very simple things, behavioral level and data flow level may be one and the same. Okay, this is what it is. Then when you are doing behavioral simulation, what is required to be given to the design code. Now what is given as an input to the simulation environment is the design code which has been written over here. Design is done in terms of module. A module is a unit of design in Verilog. Just as the unit of functionality in a C language is a function, with all functions being named differently except one function which is called the main, which needs to have that particular name, fixed main function. Module in Verilog doesn't need to have a fixed name. It can be any meaningful name, a module, except that it has got certain rules which we need to follow. The module name cannot start with a numeral, it has to start with an alpha character only. Okay, that is what it is. Test bench. Test bench, which was developed by the verification team. Now verification team has, as I said earlier, has got about 2.5 times the strength of the design team. So verification team is a kind of a job which is a very, very responsible job, because if, God forbid, something is detected after the chip has been manufactured, some problem is coming in the chip after it has been manufactured and it is not working correctly in a particular situation. If that happens, then there is an analysis made of whether such a test has been done for this particular situation or not. If it says, if it is found that there has been no test which has been developed or which has been created for this kind of a situation, which shows a failure in the field means at the end user's site, then the verification team is really taken to task. It would also mean a loss of job for the verification manager. It could mean, not always it does happen, but it could mean, depending upon the seriousness of the situation. If the company is looking to capture the market with this particular product, and then it is seen that this product has got some defects inside, then a respec spin of this particular chip is required, millions and millions of dollars would be required to be spent once more, okay, and that would erode into the profits of that organization. So that's a serious view that the management takes about the loss. Loss means loss of money that has happened. Why has it happened? Because the verification team was not responsible enough for creating tests for the various scenarios. It failed to imagine or visualize that all these are various scenarios for which test cases have to be written. And I have heard of situations where the verification manager had to quit because he or she was asked to quit because of such issues. So it's a very serious or a very important role that a verification team has to play in the whole manufacturing flow. And many a times, unless the verification manager signs off and says that okay, verification is now complete and all the situations have been covered, that means for all the specifications there exists at least one test which will cover the specification. At that time he signs off and says yes, verification is complete. He says verification is complete and the responsibility of that is on his shoulders. Okay, he doesn't say that there are no bugs, he says that verification is complete. Now once that is done, then the next steps, then the layout process is kind of frozen or finalized only when the verification is completed. Now this activity between the design entry and the test bench writing goes on in parallel. I want all of you to understand how the things go on in an organization. I could have just run through the flow and saying that from here it comes here, from here it comes here, and from here it comes here. If the objective is met, then it goes to the next step, otherwise one. No, that's not the intention. The intention is to give you a nice idea of how development takes place. Okay, so these activities go on in parallel, and when the design is reasonably ready for verification, a simulation is run on that. The test bench which was developed for every block will have its own test bench. At the block level testing, that is what is known as the unit level testing or verification, not testing. There is a difference between verification and testing. Okay. So verification is done at the block level, and then later on it is also done at the top level. Top level means you integrate several blocks together and then perform a verification or at the top level to find out whether these blocks are interacting correctly or not. Each of these blocks may be doing its functionality properly, but if they are put together when they are not working, they are not interacting properly, the communication between the blocks is not correct, then when the blocks are integrated together, they will not work correctly. So that top level simulation is also done at a later time, but here this block level simulation is done. For simulation, the test bench is written, and that when the test bench is written, what does the test bench contain? It contains code which actually houses the design and applies the inputs called stimulus. Stimulation is different, simulation is different. What is simulation? Simulation is running in software a model which mimics or kind of captures the functionality of the block that is supposed to be there after the block has gone into silicon. That is simulation, completely running in software and capturing in software and verifying in software the behavior of that block that would exist after it has been manufactured. So right up front in software, we are capturing the behavior through a model and trying to verify that behavior, because here it is much less expensive to make changes in the software compared to the changes required to be made after the chip has been manufactured. Very expensive. So therefore this is done. And stimulus means applying the inputs, exercising the design with different types of data, with different types of scenarios, combinations of data and address, if this happens to be some kind of a processor or whatever it is, or some control inputs, combination of control inputs, all possible and allowable and valid combinations of inputs are given from the test bench to the behavioral simulation, which takes in a design code, it takes in a test bench. Okay, the test bench actually houses the design and then it executes the simulation. It executes the simulation. What is the objective of simulation? To find out whether it is working correctly or not. Okay. Overall, at the block level simulation, you have several tests to verify the functionality. Have all those tests been met or not? Is the objective being met or not? If the answer is yes, we will see what is the objective. But if the answer is yes, then you go to the next step. This can be shown only like this, okay, in a block diagram, but whereas the actual execution happens differently from how it's shown in the block diagram. Block diagram is good because you cannot express or show concurrency so easily in a block diagram. Therefore, in order to make you understand the flow, I have drawn the block diagram, but in actual practice the execution is slightly different. So, if the objective is not met, then again you go and do simulations after making changes either to the test bench or to the design. Test bench is a piece of design, is a piece of code. Test bench is also a piece of code. Now, the design has to be verified by the test bench. What is the guarantee that the test bench is not written correctly, has been written correctly? There is no guarantee. So, there is a problem with the test bench, could be a problem with the test bench, or it could be a problem with the design. Then both these teams sit together, thrash out the problem. In case there is a contention or that test bench, the verification team says there is no problem in the test bench code, the design team says there is no problem in the design code. There is a deadlock situation. So, who comes and resolves this situation? Project manager, the chip lead, the person who is responsible for the manufacturing of the chip. He will do it personally, or he may assign this task to somebody to mediate, okay, between this, or arbitrate between this and come to a resolution as to what the specification actually means, and from there they will then know whether the problem is in the test bench or the problem is in the design code. Okay. Then that is rectified, and once again the simulation is run to find out whether the objectives have been met or not. Like this, the whole process goes on in a continuous iteration like this. It goes on in a continuous iteration. If the objective has not been met, okay, there could be a problem in the, maybe a small problem which has occurred. Okay. So, you may have to run the simulation once again, okay, without changing the design code. The test bench may have a problem, or it is possible that the design has got a problem, therefore you change the design code, run the simulation once again, and hundreds of times this iteration will keep going on and on and on. So, at the top level, what is the objective that needs to be met? Assuming that this flow is meant for the entire chip, not for simple block like this entire chip. Okay. What are the verification metrics? Metric is a measure of performance. Okay. Metric is like a yardstick, okay, which you use to measure something. Okay. So, therefore, the verification must see to it that when you are exercising the design and the design has got Verilog code, it must exercise the design in all possible ways, so that there is nothing left to be not exercised, nothing left to be exercised, sorry. Okay. Therefore, we have these various metrics which are there. Statement coverage. Now, there are tools, the verification, the simulation tool simulator will have a mechanism to find out how many times a particular statement is executed, if it is executed at least once or not. Okay. Like that, it is what is known as, you have to profile the code. You have to include an option called coverage option in a simulation when you run the simulation, so that the simulator will it will take slightly more time, but it will gather information about which statements are executed in the design code. The design code needs to be exercised completely by the test bench. So, that will let you know what is this statement coverage, how many statements are there, has each statement been exercised at least once or not. That is the statement coverage. The other thing is the branch coverage. Now, when you say branch coverage, if else conditions are there. If you enter an if loop, or if else loop, or if you enter into a case statement, there might be multi-way branching. Okay, have all these branches been executed or not? Okay, so therefore the statement coverage itself may not be sufficient. Branch coverage is also important, whether all these branches have been covered or not. Okay, then expression coverage is another metric for I will maybe later on I will show you a verification report which shows how much percentage of each of these metrics have been covered, okay, based on the test bench and the design that has been used in that particular case. I will not go through the design, I will just go through the report to show you how the report looks like, a typical report looks like. So expression coverage is another thing. For example, if you have something called y is equal to A or B or C, where OR means logical ORing. A, let's say, is an 8-bit quantity or a single bit quantity for simple sake. B is a single bit quantity and a C is a single bit quantity. Therefore, y is equal to A or B or C. Just visualize. I am not writing it down here. Then the expression coverage indicates y will become 1 when either A is 1 or B is 1 or C is 1 or more than one of these quantities is 1. So now expression coverage tries to see whether y has become 1 due to A, whether y has become 1 due to B only, or y has become 1 due to C only. That means when A and B are 0, C is 1, or A is 1 and B, C are 0, and A and C are 0 and B is 1. So it will try to find out, it will check whether the expression for y is becoming 1 because of A alone, because of B alone, because of C alone. Just because y is equal to A or B or C has been executed once, that is not sufficient. The verification must also cover the possibility that y becomes 1 because of A, it becomes 1 because of B independently, and it becomes 1 because of C independently. That is what is meant by expression coverage. FSM coverage. What is FSM? Finite state machine. You may have a finite state machine inside your design and you may have several states. Now, is the stimulus, the inputs, are these inputs extensive enough to cause all the states of your state machine to get covered? S1, S2, S3, S4, S5, S7, all these states might be there. They must get covered at least once. That means they must, the design must visit each state at least once. Not only that, in addition to coverage of states, arc coverage. Arc coverage means has every possible transition from each state been covered. That means you may have a state machine. Now, if you have a state machine, your state machine has been designed in a particular way. Let's say there are 4 states in a state machine, and let's say it is your state machine has got some transitions from one state to the other state. Theoretically, from each of these states you can go to 3 other states. From each of these states you can go to 3 other states. Therefore, the total number of transitions theoretically will be about 12. 4 states are there. From each of the state, either you can remain in that state or you can go to 3 other states. So ideally speaking, not just 3 transitions but 4 transitions, because a particular state can remain in that condition for a long time. Therefore, there are 16 possible transitions, but your state machine may not have all the 16 transitions, because your state machine has got a certain job to do and your state transitions have been are there according to that functionality. So therefore, not all 16 transitions may get covered. So you may not have certain transitions being shown as covered. They will say that this transition has been not covered, but then you must say that yeah, this is not expected to be covered in that particular state machine because the design does not have such a transition in place. So you have to kind of right there saying that these transitions are okay. Even if these transitions are not covered, it is kind of an okay. So that has to be done by the verification team lead. So these objectives, but finally what is the most important in the current day situation is the functional coverage. Functional coverage means what? Okay, now these things can be done. Okay, these were more or less like things of maybe the yesteryears. Yesteryears means a few years before. These were important. I am not saying that these are not important right now. These continue to be there, but what has gained importance these days in the verification is a functional coverage. What is functional coverage? Functional coverage means that the verification team lists out all possible scenarios in the verification that can be exercised, that can be with which the design can be verified or tested. So such scenarios, based on the specification, they come out with a complete list of scenarios saying that this situation is there, so many different situations are there, and for every situation, for every combination of inputs which represents maybe a situation, there must be a test, and therefore the specifications have to be fully exhausted and all possible combinations of the inputs and different scenarios must be listed out. And for each scenario you must be having a test to verify whether that scenario is working or not. Now for example, what scenarios could be for a cell phone? Let's say that while you are listening to music, messages also should come in. Okay, or maybe your call should come, it should stop the music. If you are getting a call, the call must come, the music must be stopped, and the music must be restored after you answer the call or you cut the call, whatever it is. Okay, so this is a particular functionality, a scenario. Therefore the verification team must write a test to see that the music is being played, okay, and then it must generate that particular input to simulate the situation that a call is coming, okay, and then the music must be stopped at that point of time. After some time, when the call is completed, the music must restore from the point from where it has been stopped. All these things have to be taken care of by the verification team. I am just giving an example. There could be several such examples, several such scenarios that exist. Therefore it comes up with what is known as a list of features or a list of tests which cover all the specifications given in the specifications document, all the scenarios, not just the specification, because specifications may say something, you will have to create a scenario from the specifications. Okay, specifications may not always explicitly say that this should be possible, but from the specifications you may have to generate scenarios. Okay, so a list of all these tests is made, and then tests are written for each and every of these scenarios. Then functional coverage says every time you run a test and that test passes, okay, the functional coverage report or the functional coverage team will tick off saying that okay, this test has been run on this particular design and that test has passed. Okay, like that, when you come to a situation where all the tests which have been listed initially in the specification, in the verification document, verification team will create a verification document listing out all the possible features and the tests in the test bench, test number 1, test number 2, test number 10, test number 15, okay, all these things it will list out, and then it will tick all the boxes saying that this has been done, that has been done, that has been done. Once it comes to that point, then it says it checks whether all the scenarios once again has been covered or not, and then at that point of time they say that verification is complete. In between there might be so many different instances where the code will have to be modified. The code will have to be modified. Now once the code is modified because a particular test is not passing and therefore the design team says that the code has been modified, it is not sufficient to run only that test and say that now this test is passing so everything is okay. No, that's the biggest mistake that a verification team could be doing. because what is the guarantee that the code that has been modified has not caused a breakage of something else somewhere else? That could have broken the code somewhere else. It could have caused some other test to fail. Therefore, once you make the slightest change in the code, all the tests or perhaps most of the tests need to be run once again on that particular modified code, and that is what is known as regression. Regression testing has to be done every time a code is changed. May not be all the tests, but the verification team may identify that these are the representative tests that need to be done and that need to be executed on the design code in order to ensure that nothing else is broken anywhere else or nothing else is broken. So that needs to be done, and that is what is known as regression. Regression keeps continuing till almost the end of the manufacturing cycle. Okay, it's not as if the verification is over and therefore the verification team, yes, verification team's job is mostly done, but there might be cases which come from down the line, downstream flow also, in which case the verification team may once again be required to write or modify a particular test case, because there might be a change in the specification. There might be a change in the spec. It's sometimes what happens is like this: you go into you're decided to manufacture a chip, and later on when the place and route is being done, it is found, it might happen sometimes, it is found that the area which has been decided before by the management, because management decides the area because that is going to determine the cost, it is not enough to do place and route. There are two calls that can be taken here. One is you increase the area. You increase the area and therefore you increase the cost for the chip, and that cost increase is there for everybody to bear. Everybody means all the customers have to bear that increased cost if they at all decide to go with that cost. Otherwise, the other call by the management is to, there could be some functionality on the chip, okay, which may be used only by 5% of the customer base. The customer base is there, let's say, consisting of Samsung, HTC, Oppo, and all these, to name a few cell phone companies. 5% of the customer base is only using this functionality. So then what the call taken by the management is, you strip off the this particular functionality from that particular design and see whether you will be able to manage with this reduced area or reduced logic. If they are able to manage, fine, they will let go of that functionality and let go of this 5% of the customer base, because they don't want the remaining 95% of the customer base to get affected by the increased cost. That might have an effect on their profitability. So basically this is a call that is taken by the management when the place and route team comes up with a problem like this. The place and route team doesn't take the call. It tries its best to do alternative ways of doing place and route, but when it fails, okay, it has to bring it to the notice of the management. Then the management takes a call whether it is indeed possible or not. When it is convinced that it is not possible, then they will decide whether to let go of some functionality or to increase the size of the silicon chip. So this is how the whole process of simulation happens, and while the simulation is going on, this code which has been written here and may not have been finalized, frozen or crystallized, okay, they say frozen because now you don't change. Anything that is frozen typically will last for a long time and doesn't change, because the metabolic activity has come down to almost zero. Therefore, frozen code is, or the code which is under development and not still frozen, is given to the downstream team, the synthesis team, so that the synthesis team will take this code and start working on the synthesis scripts. Why I am saying script is basically because it is always desirable to automate the flow, the entire manufacturing or the entire development flow as far as possible. It is good to be able to automate this, because then you can run this even when you are not present at your workstation. Even in your absence, you just fire a particular script or start executing a particular script, and that will run throughout the night, and you come in the morning and collect your results. Okay, that is the advantage of automating. Now, simulation. What is meant by simulation and what is meant by emulation? Let's have a look at the next slide. I have given you an overview of simulation, okay, and I want to give you the difference between simulation and emulation. Okay, simulation is verifying the functionality of some logic entirely in software by running it on a processor. One single processor like an x86, okay, will execute the functionality, and therefore such a verification done entirely in software is what is known as simulation. Emulation is verifying the functionality of a logic circuit by making a design run on another piece of hardware. This is entirely in software and this is another piece of hardware. For example, if you have developed a new microprocessor or new microcontroller, a 4-bit microcontroller with some specialized instructions, okay, for use in let's say a FMCG product, FMCG. Okay, you know what is meant by FMCG? Fast moving consumer goods. That is FMCG market, for the FMCG market. Suppose you want to develop and you say that it's going to sell in hundreds of millions all across the world. So, if you want to verify the functionality of that particular microcontroller, you may have done so in simulation, but if you want to really check whether it's going to work correctly in hardware at very little extra cost, what you would do is you would take this Verilog code or whatever it is for the microcontroller that you have written, okay, and put that particular design, synthesize it, target it to an FPGA and put that microcontroller design inside an FPGA. So now what you are doing is you are taking the FPGA. FPGA works as a platform for verification of your design. Now this is a completely hardware thing. You don't write a program in assembly language for an FPGA. An FPGA executes the design directly. It executes the design directly, whereas a microprocessor or a microcontroller executes your function through a series of assembly language routines or through a series of instructions. The same microcontroller, if you are putting it over here, then you are trying to see whether your microcontroller is working correctly in hardware or not. It is not the ASIC, but it is the FPGA on which your microcontroller is sitting. Sitting means it's residing inside the FPGA, and the FPGA also has got a memory. Therefore, this memory will store the instructions for execution by that particular processor. Therefore, the verification of a logic function by making that logic function execute on a different platform is an emulation. Making it execute completely in software is simulation. Simulation is much slower compared to emulation. Okay. Now, 10 microseconds or a 10-second program will run in 10 seconds on an emulation platform, but a 10-second program of a microcontroller might take maybe several minutes or several hours to run when it is run in simulation. That is the difference. So, emulation is almost always real time, whereas simulation is not real time because it gets executed in software on a single processor. This gets executed on a different platform and this runs in real time. That's the difference between simulation and emulation. Languages used for describing hardware are Verilog, VHDL and system Verilog. I have already told you the importance of verification. The importance of verification is that verification these days has got certain standards to which you must comply, you must adhere. You means anybody who is doing verification. It should be possible to easily port a verification environment from one processor to another processor. These standards have evolved, emerged, and are more or less solidified, now crystallized, with system Verilog taking a key position in this verification standardization, and that being the language used in the verification environment. Almost all standard verification test benches, when I say test benches, it means verification test benches, are written today using System Verilog. Okay. System Verilog is the language of this test bench, and UVM, Universal Verification Methodology, okay, is the standard methodology that provides the framework for the verification test bench. Okay. That is the standard that has evolved and come to stay. Most of the companies use UVM as a standard because it has become an industry standard, and it becomes easy for your verification components to move from one platform to another platform. Also, companies these days are generating what is known as verification IPs, not just design IPs but verification IPs. Okay. And therefore, verification is become a very standard setup in the whole industry today. Okay. We will see later on how to write a small test bench for verification of the design. Obviously, I am not going to go into System Verilog and UVM because that is something which cannot be explained in such a short time. I have just mentioned all that you can know about System Verilog and UVM here is only the spelling. Nothing more than that you will be able to know in this such a short time. So, writing a test bench for verification of the design is what we will see later. I have come to a point in time where I am open to taking questions from the viewers, and if you have any questions you can go ahead and ask. Till such time that the question comes, I will go ahead with my next slide of presentation. In this slide, I have shown you what is meant by a self-checking test bench. For small designs, many a time you write a test bench, you run the test bench on the design, and then you see the output through a waveform or through some values that are printed on the console, that appear on the console. Okay. And from those values, then you apply your own judgment to these values and tell whether these are expected values or not. Whatever you can do mentally sitting there in front of the terminal can also be done using logic in the test bench, such a way that the test bench itself determines whether the output obtained from the design is correct or not. Now, for do that, you need to have a comparison of this output with the expected output. How will you compute the expected output? You need to know what is expected. If you don't know what is expected, you cannot judge and you cannot pass a judgment on whether the output is right or wrong. Suppose I give an exam in Verilog, okay, and people answer the questions in Verilog. The answer scripts come back to me. I know what is the expected answer, and if the answer is closely matching with the expected answer, then the student gets good marks. Otherwise, if the answer is not as per the expected answer, then the student doesn't get good marks. Okay. What happens if you give the same answer scripts to somebody who is a graduate in biology or chemistry and doesn't know Verilog? That person may not even be able to pass a judgment because he does not know what to expect. Therefore, a judgment can be passed only when you know what to expect and what is obtained. You compare the two quantities and pass a judgment whether it is failed or passed. The same thing that you do mentally can also be done in a program, and such a logic which is incorporated into the test bench is what is known as a self-checking test bench, which give the results of the running the tests on the design. This itself gives the result. You don't need to really sit there and analyze each and every waveform. That analysis you put in the test bench itself. Okay. In the case of a self-checking test bench, is not required to check the results of the test manually. It will be done automatically by the test. Automatically means it will be done by the test benches because you have provided that capability in the test bench. Okay. What does verification do? Verification checks to see if the intent of the specification is captured in the design. That is what is verification. It is different from testing because testing means, if you go by the pure word of testing, it means that you are trying to see whether a particular design has been manufactured correctly or not. that testing means manufacturing testing, whereas verification means trying to see whether the intent of the specification, whatever specification was given to the design group, whether it has been captured in the design correctly or not. Now, in big projects, this is not done manually. The discussion doesn't go on manually between the verification team and the design team. What happens is there is a bug tracking software whose names I have mentioned here. Okay, I have had the experience of working on Bugzilla. Bugzilla is a software which keeps track of the bugs. The verification team enters the bugs which have been found in the design, okay, and it assigns it to the verification manager or any verification person. If it is assigned to the verification manager, then the verification manager will assign it to the concerned person, okay, in his team or her team. Then the verification engineer must also create a test case, okay, which shows where the problem is occurring. So the design engineer will take this test case and run it on the design and say that, okay, there is a problem in the design or there is a problem in the test case. Okay. Therefore, a test case must be created, or a situation must be created for the design engineer to handle this bug properly. Once this bug is handled and addressed and issued, the design engineer will put it back to the verification engineer, who only then can close this particular ticket. There is a ticket that is generated every time there is a bug that is reported. Okay, so these tickets are kept track of. Therefore, you know at the end of the whole project how many such tickets have been generated. If a ticket is falsely generated, okay, it can be perhaps deleted, but this data can be useful in creating a lot of history for this product. History means in collecting data, this will be useful for the later projects down the line. That this particular project had got, let's say, 4075 bugs or whatever it is, or 475 bugs. 4075 bugs is not having a good name, not giving good chit to the design engineers. 475 bugs, let us say. These 475 bugs for this type of design is typically what I would expect the first time around. Next time around, if you want to design something very similar to this, you should expect lesser number of bugs. Not 475, maybe only 100 bugs, because some of the bugs which have been there which have gone into the earlier design, the solution for that has already been found out and it is residing in the minds of the design engineers, so that it is expected that these design engineers will not create or will not such a bug will not get generated once again. So therefore, this is useful in estimating what will be the schedule for the later project, okay, something of a similar nature or maybe of a different nature, whatever it is, but this is important data. Okay, so some of the bug resolution software is backlog from one company. I don't remember the name of the company, Zoho and Bugzilla, and these are some of the software which track bugs. One of the other software which I have not mentioned over here is also the software for version control. Version control means as you keep revising your design, okay, there are several people who are working in the team who are using your particular design. Now, if you put your design and put the design in one place and the design is faulty, it will cause a lot of problems to other people which are using your design in some way or the other. Therefore, you should not put faulty versions of your design open to public use, open to use by other team members. You must locally work on that design, ensure that, or at least be confident enough that the design is not going to create problems for the others. Then you can put it inside what is known as a repository, so that other people on the design team will be able to use that design. So today we have seen how the simulation process actually goes on and what are the simulation teams, the design team and the verification team looks like. Okay, I thought of covering this particular slide, one or two slides also, like giving you the details of the names of some of the EDA tool vendors and some of the tools that are used in the design. but however we have run out of our scheduled time. So I'll carry this over to the next session tomorrow, being the 5th day of this training program. And for here I will stop now. I have not received any questions for this session. I had thrown the session open 10 minutes earlier. Because I didn't receive any questions, I went on with my presentation. And if you have any questions, you can raise these questions through mail, or you can raise these questions tomorrow at the end of the session. For now, it's bye-bye from me. Namaste. Have a great day ahead, and I hope to see you, all of you, tomorrow. Thank you very much.
ఆరోగ్యమిత్ర వెన్నునొప్పి రావడానికి గల కారణాలేమిటి? సర్వైకల్ స్పాండిలోసిస్ లక్షణాలు